So I'm just going to work through the solution to this problem. So the question is, a biomass furnace burns a wood chip fuel, and you're given the composition of that fuel. Okay, you don't know what it is, but it doesn't really matter. You're just told the ratio of carbon to hydrogen to oxygen. And the first thing that you have to do is write a balanced chemical equation for the combustion of this biomass with air. You need to do that in a way to do the second part of the question, but obviously just stating explicitly that's what you have to do. Then in the second part of the question, you're told that a dry sample with a flue gas is found to contain 14% carbon dioxide and 7% oxygen by volume, and you're asked to determine the actual gravimetric air to fuel ratio of the combustible mixture with air. Okay, so this is how you solve it. So first of all, you need to write a balanced equation for the stoichiometric combustion of the wood chips. And the method you should use for this is the method that I taught you in the combustion videos and lecture. So if you're not sure, go back and look at that. But the process is always start with 1 unit of fuel. So that's our wood chips here. React it with some air, you don't know how much. And that gives you some carbon dioxide, some water, and obviously the balance of nitrogen at the end. So remember I told you to write out the table where you got the reactants and the products, and you got carbon, hydrogen, and oxygen. Then you got 6 carbons on this side, 10 hydrogens, and the number of oxygens that you have is you have 2x from the air and 5 from your fuel, so it's 2x plus 5. The amount of carbons you have on this side is y from the carbon dioxide. Number of hydrogens you have is 2z from the water, and the combined oxygen in the carbon dioxide and water is 2y plus z. So now we have 3 equations, 3 unknowns, so we can solve for this. Y is 6, 2z has got to equal 10, therefore z equals 5. Therefore, if we plug that into y and z into this equation, we should have 17 oxygens on this side. If we have 17 oxygens on this side, we must have 17 oxygens on this side, and then 2x plus 5 equals 17, x is equal to 6. And if we plug x, y and z back into the equation at the top, then we end up with our nice balanced equation for the combustion of this wood chip in air, and not forgetting that we need to have the nitrogen on the other side for it to balance. Okay, so that was from the previous slide. So that's the first part of the question, which you need to do in a way to solve the second part of the question. And so we have the stoichiometric combustion of our wood chips with air. Now we're told it burns with excess air, so we're not sure how much, so we're going to use a big X to show that this is burning with excess air. So we know for stoichiometric conditions it needs 6 units of oxygen, but we've got excess units of oxygen, so X is greater than 1. And what that gives us in our exhaust is it gives us the same number of carbon dioxide, because we haven't got any more carbon, same amount of water, because we haven't got any more hydrogen, excess nitrogen, and the remainder of air. And remember, it's X minus 1, because 6 units of oxygen is being used to create the carbon dioxide and the water, and the remainder, so the X minus 1, is what's left over. And just to reiterate, just remember the check is that if you set x is equal to 1, so this becomes 6, then x in this term, x minus 1 becomes 0, so this term will disappear. So you end up with this equation at the top for complete combustion. Okay, so algebraically this is what we have in terms of the excess air. Now the number of moles in the dry exhaust is 6 from the carbon dioxide. It's dry, so we do not include the number of moles from the water. 6x 79 over 21 from the nitrogen, and 6x minus 1 from the excess oxygen. So this is the total number of moles in the dry exhaust. Now, if you remember from the question, it said that we had 14% carbon dioxide. So we know that 0.14 is equal to the number of moles of carbon dioxide, which in this case is 6, divided by the number of moles in the dry exhaust, which we just shown there. So now we've got one equation, one unknown, so we can solve for x. And if we solve for x, it comes out as 1.5, and we can plug that back into our equation, and now we've ended up with a nice balanced equation, but with excess oxygen. So this wasn't quite finished. We haven't quite finished the problem. In the original question, we were asked for the gravimetric air to fuel ratio, and at the minute we've just got that ratio in terms of moles. So we need to get it into by mass. And simply the way that we do that is we times by the atomic masses. So remembering that carbon is 12 grams per mole, hydrogen is 1 gram per mole, oxygen is 16 grams per mole, and nitrogen is 14 grams per mole. So if we want to find out the air to fuel ratio, we set the fuel against the air, put in the atomic masses, basically just run it through the calculators, and you should end up with a gravimetric air to fuel ratio of 7.6 to 1.